Okay, so in this course, we will learn the analysis of algorithms. Okay, so this is different than what kind of thing you have learned earlier. Like you have coded probably in 271 some basic sorting algorithms in data structure, maybe some searching and more advanced sorting algorithms and stuff, and maybe binary search tree. But here, what we know. That yes, there are algorithms, there are programs which are kind of codification of algorithms. I mean, programming in programming languages. But here, what we learn more is the analysis of algorithm. How would you tell, seeing an algorithm or seeing the pseudocode of an algorithm, that whether this algorithm is efficient or not? Or given, suppose for insertion sort, I give you like 5 different algorithms for doing insertion sort, or 5 different algorithms for sorting among them. How will you tell, okay, one is better than the others? Okay, so now see, there is a catch here, that suppose I design a very stupid, poor algorithm, like bubble sort. I don't know, you know bubble sort or not. It's a very inefficient algorithm for sorting, and I run it on a supercomputer on a same data set. Same data, I mean a given data set, and on the same data set you also run your algorithm, okay, which is probably a very efficient algorithm, and you run it on, probably you do not have a big computer or you do not have bigger resources, so you run it on a small laptop machine or a tablet computer or even a smartphone. Okay, so see the problem. So it's a same data set. I have a stupid algorithm, you have a good algorithm. I run my algorithm on a supercomputer or a very high-end, high-power machine, and you run your efficient algorithm on the same data set on a small computer. So definitely the supercomputer will win in that case. Okay, I am saying definitely, but it is theoretically not definitely. It's more like practically definitely. Okay, so why theoretically not definitely, I will explain to you. But before that, you see that in all sense of practical knowledge, we can say that no, definitely a mobile phone or a tablet computer will be beaten by a workstation, okay, for sufficiently large, very large, like 50,000 number we're trying to sort. So but so that means we need a common platform. Okay, this kind of very disparate resources will not be able to tell that, okay, your algorithm is better or my algorithm is better, or my stupid algorithm running on a workstation, still it's poor than your intelligent algorithm running on a smartphone, or things like that. So the platform is an important thing when we are running computing on certain resources. Okay, so we say that we need a common platform to put, run all such different algorithms on a generic, common, realistic environment, and then only we can say, okay, in this generic environment, my stupid algorithm performs slower than your intelligent algorithm, so your algorithm is better than mine. Okay, so in order to design such a common platform, it is a model is proposed. It's called a RAM model. Let's go through this. So analyzing an algorithm is about predicting the resources that the algorithm requires. Okay, so what are the resources when your computer requires when you are trying to run a large program or something, any program? So the resources are like memory. Memory is a resource. You may remember when I'm talking about insertion sort, that insertion sort is the in-place sort. So whatever be the memory given to the insertion sort, the input sequence, so it is actually using the same memory. It is not even taking some extra memory. So that's like trying to save memory, in memory, or in-place sort. But this is this is like what are the real hardware resources it is needed to execute the program. What about the bandwidth? Okay, it's a network bandwidth. Okay, bandwidth. And then what about the processing power or other hardware resources? What will be necessary for a computer? This you understand. Okay, so the computing resources to we are trying to predict, or you are trying to kind of make a trend. Okay, this is the algorithm, so this will be the running time or the the resources required. So so now the model of the implementation technology. So we need a model for this kind of technology, okay? Because I have a laptop which have certain resources, and you have a different laptop which may be advanced or maybe older. So it's all a disparate resources. So we need a common technology model, and within that model we also need the model for the resources, like what kind of memory it has, or what kind of instructions it executes, or what kind of resources it is supporting, and also the cost model. Okay, so what is the cost for executing a particular instruction on that machine? So we need all these models to create a common platform, a unified platform for executing all such algorithms. So what we need first is the model of the implementation technology. Okay, what kind of implementation technology we are using for the model. The second is is the model for the resources, individual resources within that technology. Okay, so and then the last one is the cost model, that what is the statement executing on such a model is costing. What is the cost? Time cost. Here cost means the time cost mostly. Okay, so we consider a generic one processor. Okay, so please remember this is one processor random access machine. So it's a simplest machine on which, so one processor here means that you execute the instruction sequentially. You do not have any parallel processing. Okay, multiple processing. So multi-threading might be allowed, but those kind of things we do not discuss much. We just say, okay, one instruction comes, executed, then the next instruction comes. So sequential instruction. So it's very simply we say that it's a sequential non-concurrent execution. Okay, so that's why we consider it's a one processor machine, because if it's a machine doing a parallel processing, two parts of the array are sorted different, by two different processors, then they are merged, definitely it will be at least twice faster. Can be theoretically twice faster, practically maybe not. But so we do not allow concurrency. Okay, so then also, like this part, model for the resources, we should precisely define every instruction of the RAM machine. Okay, so like assume that in some computer, I am assuming I have a computer which can sort the button click on button click. So I have a button that says sort. I click it and it's sorted, maybe as big number like 1 billion number array. But this is practically not possible. You have to understand, I cannot make this kind of assumption to make sure my algorithm runs fast. Whatever be the, even if it's the button click is there should be multiple instructions at the lower level which will actually make it happen. Okay, so so we have to make some realistic assumptions. Okay, so technically we should define every instructions of the RAM machine, but that's not practically possible. Like in a instruction set architecture of standard processors like Intel or Athlon, AMD. So they have so many instructions, so much detail. We cannot just define every instruction. Like we can probably, but that actually outweighs our study of algorithms, and we become the processor analysis or processor instruction set architecture design study. But we do not want to do that. We want to make some generic high level assumptions. Computer science is the science of abstraction. Okay, we want to make some abstract assumption which will be realistic as well. Okay, so we make the some realistic assumption like arithmetic instruction. We make the assumption that okay, we have standard arithmetic instructions like plus, addition, subtraction, multiplication, division, modulus operator, floor, ceiling, all this kind of thing, which are in every standard computing device. This kind of formulations, this kind of instructions are there. We just make that our RAM model is a computing machine which supports this kind of arithmetic instruction. Now, what about the data movement type instruction? Data movement are instructions where from processor to memory, memory to processor, how the data is being moved. The standard instructions are load, store, or copy. Okay, so we say that okay, you do either load instruction from memory to processor, store instruction from processor to memory, copy instruction from memory to processor, or between registers. So all this kind of data movement operations are possible. They are standard and multiple machines use them. What about the control instructions? control instructions are like branch, call, or return, this kind of instructions. Okay, so like branch can be conditional or unconditional branch. Call is like a subroutine call. Return is like return from a subroutine. All these instructions, can take just constant amount of time. So that is the cost model. Here we said that the first we have the model of the implementation technology, like we say it's a random access machine model, which is a single processor model. And then we say model for the resources, we say how the instructions are being executed. We cannot model for every instruction, that is difficult. So what we do, we say that okay, they are executing or they are supporting standard arithmetic, data movement, control type of instructions. And we also make the cost model that each such instruction takes a constant amount of time. Okay, so suppose if they take like 2 time unit for executing an addition. So if there are 20 times addition being done, we can just simply multiply, say that the 2 time units and 20 times, that's 40 time units. Okay, so that will help us to count the time needed for executing a particular instruction. Now, what about the data types? Data types are a very important part of execution of algorithm and modeling this kind of abstract systems. So we say that the data types supported are integer and floating point. So using integer and floating point, we can cover most of the other things like ASCII values and stuff can be used for representing characters, and we can use integer and floating point for converting them and using them like that. So but there is a very, very important assumption which is called a limit on the size of each data word. I don't know what you know about data word. So data word is the amount of data being fetched from memory to the CPU at one go, at one instruction. Like if we execute load, so how much data from the CPU will, from the memory will come to the CPU at one time. Okay, so in standard machines of today, the data word size is like 32-bit or like 4-byte, or 64-bit, like 8-byte. Okay, so that's why we say that, oh, it's a 32-bit machine or it's a 64-bit machine. That means how much data from the memory to the CPU can be brought in one time. What is the, also we say that what's the capacity of the bus. Okay, so the bus capacity is 64-bit or 32-bit, means that much data can be brought from primary memory to CPU at one time. Now you see a very simple calculation. If there is a 8-bit data or some 8-bit value, so that needs like 2 to the power 3. So 3 bits to represent an integer with up to that much size. So 3 bit will be necessary. So this is actually, if there are we say that for inputs of size n, we assume that integers are represented by C log n bits. This is important. So you can understand that for integers, log n number of bits will be necessary. So because this is, as I said, this 2 to the power 3 bits will be needed to represent numbers 0 to 7. Okay, 8 numbers like 0 to 7 will be represented using 3 bits. So that is log n number. If you take log, so that is 3 bits. So log of 2 to the power 3 is 3. Okay, so that's a log n number of bits. Now we also say that we also multiply a constant with that. Okay, so the constant has to be greater than or equal to 1. So it is log n or more, like 3 bits or more. Okay, so now as I said, if it's c equal to 1, we make sure at least 3 bits are needed to represent an integer. This is just an example. Now the c is a constant. Okay, we assume the integer represented some constant. Why c is a constant? C is a constant because you need, a word should be big enough to hold any one number. Okay, it should be big enough. C is at least 1, so that this log n bits represent that number. But not all the numbers in one single word should be, all the numbers you should not be, like if C is like, very large number, C equal to like 5 billion or something like that, 50,000. So then what happens? All the numbers you want to put it in an array will come from the memory to the processor as a single chunk, which is practically impossible. Suppose you want to sort 50,000 numbers. So if C is 50,000 times log n, that means all the 50,000 numbers are coming from memory to processor in one go and being sorted together as a constant time single operation, because we said that each instruction takes a constant amount of time. So you can understand that this is practically not possible. So we make this assumption. We say that C log n bits will be needed to represent integers, and C is a constant greater than or equal to 1. And it is, kind of implied that C is a constant. C will be some value, but it will not be very, very large number. So that's why I write this. A word here means a memory word, what we bring from memory or the way it's stored in the memory. A word should be big enough. That's why it's greater than or equal to 1. Big enough to hold any one number, but not all the numbers in a single word. All the numbers should not be stored in a single word, which is impractical. Okay, so that's why. So this is important, very important assumption. And there are we do not model memory hierarchy in the RAM model. Okay, what does it mean? Memory hierarchy is a system where the lowest level, when you try to fetch some data from the memory, we store it initially in the registers, which is a processor real estate. That means inside the processor there will be register, which is the fastest form of memory. Quickly you can access it, but it's very costly. So the next level of memory hierarchy are the cache memories, which are faster than primary memory, but slower than the registers, processor registers. So it is more costly than the primary memory. Then the next level is the primary memory, which is bigger in size but slower than the cache. Okay, and then the next level hierarchy is the virtual memory or the secondary storage, like external portable hard disk, which will be very, very slow. Okay, like 1,000 times slower than the primary memory, but it has a much more space and is much less costly. Okay, so the memory hierarchy is not being modeled in the RAM machine because it's not necessary. Without that also we have a very good performance. That means the analysis of algorithms using RAM model is very much almost accurate. Okay, so another thing is that we want to say that we treat computations of 2 to the power k as constant time operation. What does it mean when k is a small enough positive number? Calculating 2 to the power k takes a lot of time. Okay, it's not easy computationally. We'll show algorithmically 2 to the power k it can be a exponential time algorithm for calculating that. But in some computers, 2 to the power k can be calculated using a left shift by k bits. Okay, k bit left shift means that multiplied by 2 to the power k. So every bit left shift is multiplied by 2. So 2 bit left shift means multiplied by 2 to the power 2. 3 bit left shift 2 to the power 3. In that way, k bit left shift means 2 to the power k. So, but in some computer directly give this kind of operations, left shift. Okay, logical left shift, something like that. But in general, this is a big or costly operation. So, but in RAM model, we assume that 2 to the power k can be considered as constant time operation, like those kind of machine which gives those operations like logical left shift. For them, it's a constant time operation, like this provided by the instruction set architecture. It's called instruction set. It's called ISA. Okay, instruction set architecture. So now, if the ISA has this, then for those machines this will be a constant time operation, even though in general it is not. Okay, so so here we assume for the RAM model that 2 to the power k can be calculated as in constant time, as long as k is a very small value and a positive number. Okay, so this is overall we discuss the RAM model for analysis of algorithm. Without this model, we cannot have a common platform for analyzing all the algorithms. And with the help of this, we will now analyze the cost of insertion sort using this kind of standard, simple, realistic instruction sets, and assuming that each instruction takes a constant amount of time for execution.